Keys posted for bonus quiz 1. According to the discussion instructors, a fair number of you determined the question on exam 1 to which the key error applied. That was the NO2N2O4 equilibrium. How many of you successfully explained why addition of the inert gas also was an acceptable answer? You did this in 2045, and I failed to think about it correctly when I wrote the question. I intended to have the equilibrium system contained in a piston cylinder rather than a fixed volume container. Because on adding the inert gas, if you change system volume, then you impact the equilibrium. Explanations on the key if you've not yet seen it. Now, last time, and as it relates to what you're doing in 46L Assignment 3, you study in Assignment 3 the chemistry of actually 4 salts of calcium ion. Calcium chloride, calcium hydroxide, calcium carbonate, calcium sulfate. Calcium chloride by default, because it is calcium chloride solution which you use in 46L to get calcium ion. I think the lab solution is half molar. So at the minimum, I imagine you would recognize that if I want to test for the presence of calcium ion in a solution system by precipitation, trying to get it to precipitate as the chloride is rather hopeless, because the chloride is damn soluble. So, with that, you looked at the formation and properties of calcium hydroxide, then you looked at the formation and properties of calcium carbonate, followed at last by formation and properties of calcium sulfate. What did you discover chemistry-wise? You discovered that calcium carbonate is a lot less water-soluble than calcium hydroxide. And these are each precipitates of calcium ion with a basic anion. So, if I have a basic solution system, or my solvent system is deionized water, and I want to test it for calcium ion, surely I'm going to try the addition of carbonate ion in preference to the addition of hydroxide ion, because the carbonate is much more easy to form, much less soluble than the hydroxide. But when you get into calcium sulfate, you find out something interesting. Anybody remember the recipe you used to make calcium sulfate in the laboratory? How many of you have looked at this? You're that far along in lab work. Formation, properties of calcium sulfate. Dihydrate. Common name gypsum. The main ingredient in plaster casts, plaster molds, things like that. The stuff you get if you add water to plaster of Paris. Just for fun, when you were a kid, you ever make any molds of plaster molds? No? Everybody these days is spending their time monkeying with computers. Not good. We'll get past this syndrome. The sooner the better. Interestingly enough, just a couple days ago, at long last, I saw a published report of the impact of technology on learning science. 42 chemists were part of the people interviewed. I mean, they took people from various disciplines, not necessarily chemistry. The chemists reported across the board that they realized technology in and of itself has not contributed a damn bit to learning science. Expedite doing arithmetic, no question about it. A powerful tool in the laboratory for data collection and processing, no question about it. But as you've recognized, I think by now, you know what happened to your arithmetic skills when in grade school and high school you were learning to do arithmetic with calculators? Your arithmetic skills went away. And you lost the ability to speak a very important part of our language, the numeric part. And you need to be able to speak that part in science if you're going to understand what science means. You've heard this sermon before. You'll hear it again. I'm glad to see the scientific community, those who are involved in academia and instruction, are beginning to realize this. I don't mean it to sound boastful and bragging or whatever, but when this stuff got started a number of years ago, I told them then and there, you're wrong. This is going the wrong way. I try to get people in this department to understand that putting computers in our 45 laboratory is silly. Because these people know how to use the damn computers. What they need to do is to learn chemistry. They can measure temperature with a thermometer. No need a temperature probe. And in so doing, learn how to make a measurement. When the computer makes the measurement, that takes one more thing away from what you should be learning. When the calculator does the arithmetic, that takes a big chunk away from what you should be learning. And I'm against that stuff. Because I want you to learn. That's where the future lies. I'm damn fed up with reading these stories in the newspaper about how American students are now ranked 16th internationally in competition with students from other countries in learning science and math. We should be number one. We got the best country there is. But our aims are way misplaced. Our goals are horribly chosen. Anyone who measures his or her success by how many Cadillacs he or she manages to accumulate during his lifetime or her lifetime is a total loss, a failure as a human being. Does that sound like I have a strong opinion on this? You're damn right, and I mean every bit of it. Money is something you need, but if money is what you thrive on, is money what you lust for, you are lost. Your life is going to be junk. And when these devices interfere with what you should be learning, they are misused. With good fortune, we'll get this fixed in a not too distant future. And screwballs like me can pick up the paper again and be happy because it'll say, University students of America now rise back to number one in science and math. That's what I want, because that's where it's at. All right? That'll conclude today's sermon, at least for the moment. We go back to this. As it follows from what we did last time, or what I was meaning to say about calcium sulfate, when I asked you folks, how many of you remember the mixture you made to prepare calcium sulfate in the laboratory? Anybody remember? What'd you mix up?
3 molar sulfuric acid.
3 molar sulfuric acid solution and?
0.5 molar calcium sulfate.
Yeah. and your half molar calcium chloride solution to provide your calcium ion. 3 molar sulfuric acid. Is that a rather strongly acidic system? So unlike calcium hydroxide and calcium carbonate, you can readily form calcium sulfate in strongly acidic system. Why is that true? Because sulfate ion is such a feeble base that unless you have the pH of the system very, very low, you don't have much impact at all on the solubility of calcium sulfate. Well, that leads into question 19-12, which we'll look at in a moment. To conclude this, if we have solutions containing sulfate ion 10th molar, hydroxide ion 10th molar, and carbonate ion 10th molar, then with simple KSP arithmetic, because once you fix the concentrations of the anions, then you're not paying attention to hydrolysis anymore. And of these anions, the only one to which hydrolysis would amount to a hill of beans is carbonate ion. So once you fix the molarity of these ions at 10th molar, then you can get a handle on the solubility for the corresponding salt, calcium sulfate, hydroxide, or carbonate by just playing with the KSP equilibrium. And here for calcium carbonate, find out that if the calcium ion molarity is bigger than this number, then you have the opportunity to precipitate calcium ion or test successfully for a solution containing calcium ion. Now notice I wrote if carbonate is about 10th molar. Here's a system you now know how to analyze in detail. We've given you the necessary tools in Chapter 18. Do you believe it is true to say that in this solution the carbonate ion molarity is 10th molar? Yes or no? Well, regardless of your vote, what would you do to find out? Would this help you find out? This is bicarb molarity times hydroxide ion molarity, and this is the equilibrium molarity of carbonate ion, given that this is Kb carbonate. If you find X to be a number which is sufficiently small so that when you subtract it from 0.10, you don't change 0.10, then the carbonate molarity in this stuff is 0.10. You think that's true? No. That's right. The carbonate molarity will reduce to about 0.09 something or other. But you got 2 sig figs, you can calculate the 2 sig figs. Because Kb carbonate is appreciable and its hydrolysis extent is significant. So you go to lab, you pick up this solution, and in truth you don't have carbonate at 10th molar. It's a little bit lower than 10th molar. That's why I wrote this here. Now 1912. 1912, as it is stated in the notes, is about a water solution buffered at pH 6. And asks the question, at this pH, is calcium sulfate or calcium carbonate easier to form? Now, what do we know about calcium carbonate so far? We've looked at its solubility in straight deionized water, where you wind up with a solution pH of about 10. And you get a solubility 1.4 times 10 to minus 4 molar. That's experimentally determined value, which is reported in the notes. Then we did some arithmetic on calcium carbonate solubility in water solution buffered at pH 8. And found out now that the solubility went up to about 1.1 times 10 to minus 3, if my memory's right. I think it is. So found out Now when you you cause the pH to decrease from 10 to 8, the solubility increased about 8-fold. Now we know the solubility had to increase when you went from pH 10 to 8 because you're making the solution more acidic. And the more acidic you make the solution, the more effectively you murder carbonate. The more effectively you murder carbonate, the more soluble calcium carbonate becomes. I mean, how are you going to make calcium carbonate if you kill the carbonate? You can't do it. So now I look at pH 6. So before we analyze the system, we already know that whatever the solubility is for calcium carbonate at pH 6 is bigger than 1.1 times 10 to minus 3. That's the solubility at pH 8. Because this system is 100 times more acidic than pH 8. Now then, first issue is, at this pH, is the solubility of calcium sulfate affected? The answer is no, it's not, as demonstrated. Here's Kb sulfate. It's a small number, which of course keeps with the fact that sulfate ion is a pretty weak base. Just for fun. I'm in a fun mood. Two ions with the similarity of each having a charge of -2. This is a strong base, stronger even than hydroxide ion, and therefore a hell of a lot stronger than this base. But they're each -2. Could you provide an argument at this stage of the game which is an explanation of why sulfate ion is a much weaker, more stable base, less reactive?
Is it less charge density because SO4 is
On what basis would you argue that?
SO4 is a bigger molecule.
Bigger ion. Okay. Can you write a Lewis picture for sulfate ion? Do it. Right now. Zip, zip, zip. You get these Lewis pictures? Hands up if you got it. Which Lewis picture do you like better and why?
The one on the right.
The one on the right. Why do you like the one on the right better?
There's a 0 formal charge on the sulfur.
An overall smaller degree of formal charge distribution. What property of sulfate ion is implied by the Lewis picture on the right? What's it called? Resonance. Do you believe this resonance structure for sulfate ion? I wrote it on the board. That doesn't make it valid. I can write on the board lead equals gold. That doesn't make it valid. We're going to do this kind of stuff in detail in chapter 22. In any case, at the minimum, we recognize the peripheral oxygen atoms are electronically equivalent. You accept that statement? The peripheral oxygen atoms are electronically equivalent. If resonance applies, what's the sulfur oxygen bond order? 3 halves. And given that these peripheral oxygen atoms are electronically equivalent, what is in fact What is in fact the formal charge on each peripheral oxygen? Minus a half. Minus 0.5. And oxygen is more electronegative than sulfur, is it not? You're damn right. Good deal so. So if along comes H+, and it looks at this monatomic species with a charge of -2, situated on an atom on a relative basis of low electronegativity, versus coming all over here and looking at this thing, which in fact has a formal charge of minus a half on each peripheral oxygen, what are you going to stick to? Do you believe now that the charge density of this is considerably greater than the charge density of this? Do you believe now that this stabilizes negative charge density a hell of a lot more effectively than this? Do you believe now this is a much stronger base? You betcha. And all of this is achievable by using stuff you've already learned. Because you did Lewis structures in 45. Now we're going to put them to use. And you talked about resonance in 45. And you talked about formal charge and bond length and bond order and all that stuff. And I keep telling my 2045 colleagues, unless you give these people questions and problems which invite them to put this stuff to use, it doesn't mean a damn thing. Because they're not using it for chemistry. And this is chemistry class. That's sermon number 2. Okay? So back to this. Kb sulfate, here's the chemical version of the equilibrium constant expression from which we can write the mole concentration ratio of sulfate to hydrogen sulfate ion, and at a pH of 6.0, where we put in 1.0 times 10 to minus 8 for this, and here's the Kb value, you'll get a molar concentration ratio in favor of sulfate ion of only 12,000 to 1. Which allows us to say forget hydrolysis for sulfate ion at pH 6. You can see right here that hydrolysis of sulfate ion does not become significant until you get to a pH on the order of 2. That's why we have asked you to recognize in 46 laboratory, when you dealt with sample 2AB unknowns, and you got a pH on the order of 1 to 2, you knew it had to be hydrogen sulfate ion. But you also knew that the solution now contains sulfate ion. But your job is to report the ion components of the original sample issued you. And if that sample can be a mixture, it could be a mix of sodium sulfate and sodium hydrogen sulfate. And there's no way you would be able to determine such, because we don't provide you with X-ray techniques or other methods that you could use to see by looking at a white crystalline solid if it's a mix of 2 or more different white crystalline solids whose crystal structures are very similar. So by observation you wouldn't know there's more than one salt there. Upshot, I can get solubility calcium sulfate from square root of its KSP, so I've done so. Now what about calcium carbonate? Well, let's go back to this equilibrium. And as we were discussing last time, I could use another equilibrium reaction here. I could write as the carbonate containing product, quote unquote, H2CO3. Wouldn't make any difference as long as I treat this correctly. Here's the equilibrium constant value. There's the equilibrium constant expression chemically speaking. S is the molar concentration of calcium ion, or calcium ion, and the molar concentration of calcium ion is S, the solubility of calcium carbonate. Question mark represents the molar concentration of bicarb ion, and there's the hydroxide ion molarity because we're operating at pH 6. So to resolve the issue, as we did at pH 8, we've got to see how the bicarb molarity at pH 8 relates to S, relates to the other possible forms of carbonate-containing stuff. Once again, a material balance issue. total possible carbonate-containing things, quote-unquote hydrated CO2, H2CO3 with the coats on it, bicarbonate and carbonate. So we can write S equals this, which is the sum of these, and I've already taken the liberty of scratching out carbonate. Do you think that's fair? Did we not at pH 8 find out that the bicarb concentration was 210 times bigger than the carbonate concentration? Yeah. And now this is 100 times more acidic. So if carbonate molarity doesn't mean anything at pH 8, it sure as hell doesn't mean anything at any pH lower than 8. Like pH 6. So if we recall that the molar concentration ratio of bicarb to carbonate is 210 to 1 at pH 8, what is it at pH 6? Come on. Tell me. Let this stuff talk to you. 210 to 1 at pH 8. What is it at pH 6? 21,000 to 1. Right? If you're mystified by this, hey, write it down. So this stuff talks to you. So what we need is an equilibrium consideration which interrelates, as a function of pH, the molarities of H2CO3 to bicarb. So I took Kb bicarb. I could take KaH2CO3, either one. Here it is. I write it as a concentration ratio of hydrated CO2 to bicarb and find out that at pH 6, the predominant carbonate containing stuff in the pod is hydrated CO2, no longer carbonate ion. In that, the hydrated CO2 molarity at pH 6 is 2.4 times the bicarb concentration. So, from this I know this, and from this I can write in for H2CO3 2.4 bicarbs. So I got this, and there's S. Bigger than this, isn't it? So this reminds us that if I have a system, a water solution system, whose pH is fixed at 6, calcium sulfate is easier to form. Now let's have fun. Let's put you back in the laboratory. You're dealing with a sample 5 unknown, where calcium ion is fair game. And you find by flame analysis the sample 5 unknown contains sodium ion. This yellow-orange flame, which is very intense, saying, sodium ion, I am here. So you can't get calcium ion by flame analysis. That means you got to go to precipitation. That's the only other method you have. So you make a solution of the sample because that's the first test, chemical test that you do. And you observe pH with the indicators and get a pH of 6. You go to the reagent shelf. And before you see sodium sulfate solution and sodium carbonate solution. Which do you grab so as to add to your test solution to see if you can get a precipitative calcium ion? Are you going to use the sodium sulfate solution, or are you going to use the sodium carbonate solution? Are we understanding the question? How many will use the sodium sulfate solution? How many will use the sodium carbonate solution? And I'm keeping my hand up because I'm using the sodium carbonate solution. You think that solution you just made in the laboratory is a buffer? Oh, it's a dirty question, isn't it? That solution you made in the laboratory is no buffer. As soon as you start putting carbonate in there, the pH will go to, and as the pH goes, calcium carbonate becomes much easier to form. But for those of you who opted to use the sodium sulfate, you will still be successful. But I remind you of some additional information that is in the laboratory manual, and which you should have learned by observation of precipitation of calcium sulfate. Calcium sulfate tends to form more slowly and give you larger, better defined crystals. Whereas calcium carbonate, you put together calcium ion and carbonate on the same pot, bloop, there it is. Now what happens to students when they do unknowns and they get nervous? My solution contains calcium ion. Add some sulfate. Go precipitate. Run away. Calcium ion absent. 30 seconds later, calcium sulfate forms. But they already wrote calcium ion absent. Because they were not patient. Don't do that. Quick and fast. For this solubility of calcium carbonate, how would you show that carbonate ion is in fact negligible? Now you could go back and do the bicarb to carbonate ratio, which we've already told you is 21,000 to 1. But I want a different way. What are you going to do? Show me that carbonate's negligible in this system. We know the pH, 6. What simple calculation can you do to show that carbonate ion molarity in this pot is certainly negligible? Yes! 6.2 times 10 to minus 9, that's the KSP value, equals a molar ion concentration product of calcium ion carbonate ion. The calcium ion molarity is that. Well, if I take 6.2 times 10 to minus 9 and divide it by that number, I'm getting 3 times 10 to minus 7. That's pretty damn small, don't you think? Enough said. So we proceed. Now, as far as subtopics are concerned, take a look, if you will, at page 1913 in the notes. Subtopic E, captured alteration of S by chemical methods. When I rewrite the notes, I'm changing this. I mean, everything we've been doing so far is a chemical method. So I don't know why in the hell I didn't think of that when I wrote this. What I'm really getting at here is other methods of affecting solubility above and beyond those which we have so far considered. But it's all chemical methods. But I want you please to look at this important statement. Top of page 1913. Statement in bold. The solubility S of any semi-soluble salt with a basic anion has got to be greater in acidic solution than in pure water, provided that the acidic solution is not a precipitator of the salt. Back to laboratory. How would you prepare calcium sulfate? You mix sulfuric acid solution, an acidic solution, with a source of calcium ion. Wham, out came calcium sulfate. Because even though hydrogen sulfate ion, which is the principal sulfate-containing stuff in sulfuric acid solution at 3 molar, even though hydrogen sulfate ion is obviously the source of sulfate ion, it's a pretty damn good acid, isn't it? Well, this pretty damn good acid is a precipitator of calcium sulfate, because it's a source of sulfate ion. So we have a calculation to demonstrate the validity of this statement. It's in the notes, but it's pretty straightforward and important. So to demonstrate the point, let's write Ka for hydrogen sulfate ion, which I'm sure you recall we did when we looked at analysis of sulfuric acid solution. See how to calculate the pH of sulfuric acid solution and the like. So you're familiar with this. Chemically wise, it's the hydronium ion molarity times sulfate ion molarity divided by hydrogen sulfate ion. So we are imagining that we're in the laboratory. And we have available 1.0 molar sodium hydrogen sulfate solution, which is an acidic solution. It's got a pH on the order of 1. Now then, to verify this pH, we apply this to the 1 molar sodium hydrogen sulfate solution. And the two sig figs get 0.10. The sulfate ion molarity as well as the hydronium ion molarity. Well, hydronium ion molarity 0.10 accounts for this pH. So here's a considerably acidic solution. Does this considerably acidic solution make the solubility of calcium sulfate go up or down? Makes the solubility go down, because in addition to being an acidic solution, this thing is a sulfate source. It's got a sulfate ion molarity in there of 0.10. So I write our solubility product constant expression for calcium sulfate, which is this. The solubility will be equal to the molarity of calcium ion, because in this system the only possible source of calcium ion is the dissolving of calcium sulfate itself. But here's our solvent. And in this solvent we have the dissolving of calcium sulfate as a source of sulfate ion, and we got sodium hydrogen sulfate solution, which provides a 0.10 molar contribution to the sulfate ion molarity. So now I've got what I need to solve for calcium sulfate solubility. And this gives me 9.1 times 10 to the minus 5 molar. Well, here's the solubility of calcium sulfate in straight water. 3.0 times 10 to the minus 3. That's a good deal smaller, which keeps with the statement at the top, the statement in bold. Because even though hydrogen sulfate ion is a considerably acidic species, it's a source of sulfate ion and is therefore by default a precipitator of calcium sulfate. So, let's refine the statement at the top to read, if I have a salt of limited solubility, I will guarantee that if the anion component of this salt is a stronger base than water, I will guarantee that solubility, salt solubility has got to increase if I test its solubility in a water solution, which is more acidic than straight water itself, provided the water solution does not also contain a precipitator of the salt. So, here's what we're going to do. Once again, we'll pay attention to the solubility of our good friend calcium carbonate. This time in ammonium chloride solution, 1 molar. knowing full well before I tackle this, the solubility value has got to be larger than 1.4 times 10 to minus 4 molar. That again is the water solubility of calcium carbonate in straight water. Because in this solution, I have a high concentration of ammonium ion, which is an acid that's quite weak, but is nevertheless a stronger acid than water, and therefore attacks carbonate more effectively than water. So what do I do now? I write the equation for the principal equilibrium reaction that will be established by taking calcium carbonate and saturating it in 1.0 molar ammonium chloride, with the ultimate goal being to determine the solubility of calcium carbonate. So now, calcium carbonate not with water, but with ammonium ion. That's the better acid. And it's a principal species in this solution. And if I'm doing anything quantitatively with this equilibrium, I've got to evaluate its equilibrium constant. I'll write the equilibrium constant. And immediately recognize this is a complex equilibrium. Something for which I cannot look up the equilibrium constant value. I got to calculate it. How do I calculate it? I let this thing talk to me. What does this thing say? It says I got calcium carbonate in it, which is a salt of limited solubility. That guarantees I got to have KSP calcium carbonate in the numerator as part of this equilibrium constant. And I see ammonium ion on the left and ammonia on the right. What's that say? Ka ammonium ion. So what species as yet that's part of this equilibrium have we not paid attention to? What is it? Hydroxide? Hydronium? Bicarb. Now, we know to get KSP calcium carbonate, I got to take this thing and multiply it top and bottom by carbonate ion. Calcium ion times carbonate ion gives me that. So now I'm going to have this thing with a carbonate in the denominator. Right? So I got carbonate in the denominator added to this collection of terms. And I see at a glance, if I multiply this further by hydronium ion molarity over hydronium ion molarity, or hydroxide ion molarity over hydroxide ion molarity, I can answer the question. Do it. Pick it up from this point next time.